All right, so we got done talking about polynomial division, and we kind of left off saying that one of the main reasons we use polynomial division is to factor, is to come up with the factors of a polynomial. So, for example, if I had this polynomial p of x is equal to 3x cubed minus 4x squared minus 59x plus 20, and I said that one of its factors is x minus 5, I want to complete the factorization here. So the way we could do this is by using synthetic division. So if we set up synthetic division, and then we have 5 in the little box, the coefficients are 3, negative 4, negative 59, and 20, then I just complete this, I just do this long division problem, so synthetic division problem. So I bring the 3 down, multiply by 5, that's 15. This would be 11, 55, negative 4, negative 20, and 0. So by dividing my original polynomial p of x by x minus 5, which I already knew was one of its factors, so it's good to see that the remainder is 0, just to confirm that, I end up with a quotient of 3x squared plus 11x minus 4. And then all I need to do is factor that. And that's just a quadratic, so we can factor that using our normal way of factoring quadratics. So the factors of 3 are 1 and 3. The factors of 4 are 1 and 4. However you like doing this is totally fine. I see that this is going to be a 3x squared plus 12x minus x minus 4. So 3x and then x plus 4, negative 1x plus 4. So this will factor to 3x minus 1 times x plus 4. And then, of course, if I want to write what this actual polynomial is factored, I'd have my original factor, which is given to me as x minus 5. And then these other two that I just found, so 3x minus 1 and x plus 4. So there we go. We completed the factorization of that polynomial. Now, the problem is, in order to do that, I needed to have this original factor. Otherwise, there's no other way. I do have ways of factoring polynomials of degree higher than 2. So like, we can factor quadratics all sorts of ways. And there are sometimes ways that we can factor higher degree polynomials. Like for example, right, if this here happened to be a perfect square trinomial, and then this was also a perfect square, we can then kind of separate them into 3 and 1. Sometimes, occasionally, you can have a group of 2 and a group of 2 where a common thing comes out and you can factor it. But this is a polynomial here, the one that we started with, that you can't do any of those things for. So this was the only way that we would possibly be able to factor p of x, and in order to do so, again, we needed to be given that original factor. Now that's not how things always are. Okay, so what do we do if we don't have that information? As is the case with a lot of things in math, if we're not sure about something, it's going to go back to really like simple examples. So let's factor both of these. And when we're asked what are the zeros of a function, or zeros of a polynomial, we're asking for when is the y value 0, right? And when is there an x-intercept? So I could potentially just quickly rewrite this function f of x is equal to x squared minus 2x minus 3. I want to know when is f of x 0. So I'd just write x squared minus 2x minus 3 equals 0. And I want to figure out which values of x make this true. So normal factorization, I look at the leading coefficient, it's 1 and 1. Those are the factors of 1. The constant at the end, that's 1 and 3. And so I have to see how do 3 and 1 and 1 and 3 or whatever go together in order to make negative 2. And again, this is totally, however you factor things is completely fine here, but this just ends up being x squared minus 3x plus x minus 3, and that equals 0, and then we can factor out from the first two terms in x, and we have x minus 3. If we factor out a 1 from the second two terms, we have x minus 3. This is possibly way more steps than you would ever need to do for this, because you can usually just figure it out, but x plus 1 times x minus 3 is equal to 0. And then so if I want to know what the zeros are, I use a zero product property. I say, okay, this could be 0, this could be 0. So x plus 1 could be 0, x minus 3 could be 0, and I'm left with the zeros. X is going to be the values of x that will make that function be a 0, or the corresponding zeros of that function, are -1 and +3. Okay, so that's how we go about doing that. What about the next one? So the next one is a little more tricky because now this is no longer what's known as a monic polynomial, meaning the leading coefficient is not 1, but we do it in the same way. So we take the leading coefficient of 1 and of 10, sorry, and the factors are either 1 and 10 or 2 and 5, and then the 18, and those factors are either well, they're a whole bunch of different things: 1 and 18, 3 and 6, or 2 and 9. And so we need to figure out what things go together to make this work. And I'm just looking at this, and I think it's going to be, what is it going to be? I probably should have done this one in advance. It looks like it will be is it the 9 and the 2 and the 5 and the, no, 9 and 2 is 18, that wouldn't be it. Would it be the 6 and the 2 is 12 and the 3? Yeah, that's what it's going to be. So it's going to be 10x squared minus 15x plus 12x minus 18. And again, however you want to factor this is totally fine, right? So 5x will come out here. We have 2x minus 3 remaining. And then if we take a negative 6, right, out of this, we'll have 2x minus 2x. We shouldn't, I did something wrong. So this was a minus, right? And then this was, so this was a plus, sorry. We don't take a negative out, we leave a positive out. 2x minus 3. Okay, and this is equal to 0. I forgot that step, but it's the same thing here. So now we want to know what values of x make it 0. So the factors would be 5x plus 6 and 2x minus 3. Okay, that equals 0. So that could means that, using again the zero product property, 5x plus 6 could be 0, so x could be -6/5, or 2x minus 3 could be 0, so x would then in that case be positive 3/2. So we have the values, I should write it like that, similar to the previous one, where x could be either -6/5 or positive 3/2. Now it's fairly important to notice something here. Now, and that is that these zeros here and these zeros here, they came from, at one point or another, the factors of the leading of the constant and the factors of the leading coefficient. And again, if you look at the -6/5 and the 3/2, we can find those numbers within these numbers. This is an important revelation, because if there are going to be factors, if there are going to be zeros of a polynomial, rational zeros, rational number, then they come from this information. So let's review all the things we know so far. We know about polynomial long division. We know about synthetic division is kind of like the quicker version of that. The factor and remainder theorem is they're all kind of related. And if we had to, if we needed to factor like a quadratic, we can always do that using traditional factoring if it's a factorable quadratic. And we can also sometimes traditionally factor higher degree polynomials also, like if we can group and basically factor by grouping. So in the event that we are not given a factor, and we have a higher degree polynomial and we're not given one of its factors, there needs to be some other tool that I can refer to for breaking that polynomial apart. What were the things that needed to be multiplied together to create this polynomial? And what that tool is the Rational Zeros Theorem. Okay, the Rational Zeros Theorem has kind of a long-winded kind of definition, but really it's pretty straightforward. What it says is that if f of x is a polynomial function with integral coefficients, and if p over q, a rational number in lowest terms, is a 0 of f of x, so p over q would be one of the things that x would equal in order to make the function be equal 0, then p is a factor of the constant term of f of x, meaning the term at the very end, and q is a factor of the leading coefficient of f of x, meaning the number in front of the highest degree term. Okay, now we can use the Rational Zeros Theorem in conjunction with the factor and remainder theorem to now suddenly be able to factor these higher degree polynomials that we were not given a factor for. Okay, so let's do this one example here in this video. Let's look at what this means, right? The factors of p, which are this is p, the constant at the end, they are 1 and 2. 1 and 2 are the things that could multiply together to be 2. And then we look at the factors of q, this is q. Sorry, it's not p, so I should say this is where we're getting p from, and this is where we're getting q from. But the things that make up 9 are either 1 and 9 and 3 and 3. Okay, and so what the rational zeros theorem says is that if there is gonna be a rational zero for this polynomial, it must be in this list of possible p's over q's. I should probably do a better job of writing in these braces here. So that one we have the p's. Okay, we can actually let me do this a little more systematically. Let's write what p's could be. The p's are either plus or minus, because these could be positive or -1, positive or -9, positive or -3, positive or -3. The p values are 1 and 2, positive or negative. The q values are 1, 3, and 9. Those are the different p's and q's. So the p's over the q's, then, p's over q's are any combination of p divided by q. So we take one of our p values, so we take 1, we divide it by 1, that'd be just 1. We take 1 divided by 3, that'd be 1/3. We take 1 divided by 9, that'd be 1/9. Okay? And then we take our other p value of 2 and we say, okay, it could be 2 divided by 1 or 2. It could be 2 divided by 3, or it could be 2 divided by 9. So what this says is that if this polynomial f of x has a rational zero, it must be from one of these rational zeros here. Like it has to be one of those numbers. Okay, so again, the possible p's over q's for this this polynomial, the possible rational zeros, are just 1, 1/3, 1/9, 2, 2/3, and 2/9. Okay, it has to be, if there's going to be a rational zero, it has to come from that list. So what do we do? Well, we can use synthetic division, or we can use the factor theorem to find out, is this a zero? Plus positive or -1. Are those zeros? I don't know. Let's check them. Is positive or -1/3 a zero? I don't know. Let's check them. Positive or -1/9. I don't know. And so this really is just a really systematic process. It's unfortunately kind of can be pretty tedious, but we do have these tricks, right? We have the factor theorem. So what the factor theorem says is if f of 1 is equal to 0, then that means that 1 is a zero of the polynomial. So that means I would plug in the ones, okay, minus 18 times 1 squared plus 11 times 1. All right, I'm just going to write the 1 in a different color. All right, so that would be, this would be 9, this would be minus 18, this would be plus 11, and then minus 2. Well, 9 minus 18 is -9, plus 11 is 2, minus 2 is 0. So, hey, look, this is equal to 0, and that tells me something very important. That if f of 1 is equal to 0, the factor theorem says that x minus 1 is a factor. Okay, it is a factor of f of x. Okay, and that's great. Right now, we were lucky and we happened the very first one we chose worked. If it didn't work, we'd have to go and choose another one out of this list, and we'll see that in a future example. So what do we do with this information? Well, now we just do synthetic division, because if we have one of the factors, like basically we're back to our original thing we could do at the start of this video, is if we were given one of the factors, we can factor the cubic in this case. So 1 is the value we'll use for our synthetic division. The coefficients are 9, -18, 11, -2. I'm taking those off the original polynomial. We'll bring down the 9. Then we have 9 here. We have -9 here. We have, that'd be -9 there. That'd be 2, and then 2, and then 0. So that works, right? That should be 0. Which means I've got this polynomial now, 9x squared minus 9x plus 2. Now, notice this polynomial times x minus 1 is this original polynomial. So sometimes we refer to this new polynomial here as, we call it condensed. Okay, it's part of, it's one of the factors of the original polynomial, but I want to find out what those two factors of this are. And so then I just go to traditional factoring method. So I got 1, 9, 3, 3, 1, 2. So this is going to end up being, what will this be? 2 is both negative, so it'll be 9x squared, sorry, 9x squared minus 6x minus 3x plus 2. And again, this is still all equaling 0. I mean, well, we're trying to find the factors right now, but if we wanted to, we could just find the zeros after we find the factors. So then we've got, we take a 3x out, and we have 3x minus 2. We take a 1 out, and we have a negative 1 out, sorry, and we have 3x minus 2 here. That equals 0, so our factors then are 3x minus 1 and 3x minus 2. And that gives us, that will be 0. So we have, at the end, our new polynomial, our factored polynomial, because that's what it was asking us to do, is going to be x minus 1, which is the one we found first, and then 3x minus 1, and then 3x minus 2. Okay. Now notice something interesting here, right? The rational zeros theorem says that if there are rational zeros to polynomial f of x, they come from this list right here. Well, look, I have 3 zeros here. What are these zeros? If you use the zero product property, the zeros would be 1, 1/3, and 2/3. All of those are in this list, right? So that's pretty cool thing. It gets more complicated, and we'll save that for the next video.